in organic chemistry, you are going to have some commonly used acids. And so it's helpful just to kind of review those really briefly. You're probably already familiar with hydrochloric acid and sulfuric acid, and these are often used in organic reactions. Other common organic acids that are used pretty frequently are things like acetic acid, where the acidic proton is here, and then p-toluene sulfonic acid, and you can see the proton there, and that a lot of times is abbreviated as TSOH. And so I just wanted you to be aware, if you saw those abbreviations, what they meant. Now, common strong bases used in organic chemistry are more varied in structure generally. Strong bases generally have weak conjugate acids. So when we define a strong base in organic chemistry, it's something that has a weak conjugate acid with high pKa values, right? Usually greater than 12, right? So that's normally what we see. Strong bases have a net negative charge, but not all negatively charged species are strong bases. So for example, like none of the halides we've talked about, F minus, Cl minus, Br minus, or I minus are strong bases. But some really common ones are oxygen bases. We see here sodium hydroxide, which you should be familiar with from general chemistry. And here are some other varieties of oxygen bases. Nitrogen bases pop up quite frequently. This is a sodium amide. This is lithium diisopropylamide, or amide. And then we have hydrides that pop up where we've got 2 electrons on a hydrogen, and that carries a negative charge, and so it's called a hydride. Now, carbanions are something else that we're going to see, and those are negatively charged carbon atoms, and those tend to be strong bases. So another one we're going to see are carbanions, and that's just carbon with a negative charge are going to be your strong bases. A common example is butyl lithium, which is shown here, where the lithium is the spectator ion, and that carbanion that has that negative charge there is a particularly strong base. Amines, we have triethylamine and pyridine here. These are often used as organic bases, and they're basic because they have this lone pair of electrons on the nitrogen. These are generally weaker bases since they're neutral and not negatively charged, so they tend to be weaker bases. All right, the last thing we're going to talk about in this chapter are Lewis acids and bases. A Lewis base is an electron pair donor. And a Lewis acid is a electron pair acceptor, right? Lewis bases are structurally the same as Bronsted-Lowry bases. Both have an available electron pair, okay? So when we talk about having an available electron pair, remember this is a lone pair or an electron pair in a pi bond, okay? Now, a Bronsted-Lowry base will always donate an electron pair to a proton, right? But a Lewis base donates this electron pair to anything that is electron deficient. So this is really a broader definition. Lewis acids, right, are any species that's electron deficient. And capable of accepting an electron pair, right? So you've got some examples of Lewis bases here. We've got free electrons on a hydroxide, on an alcohol. We've got a pi electron pair and a double bond. We also have noticed that Lewis acids can also be Bronsted-Lowry acids. Water is a good example, ethanol. And then you can have Lewis acids that are not Bronsted-Lowry acids. Boron and aluminum, these are generally electron deficient because they don't have that full octet there. So they only form those 3 bonds. I want us to look at some examples of Lewis base, acid-base reactions. And so let's look at the mechanism for this reaction. Okay, so in this reaction, what happens is the electrons on the oxygen will come and attack the electron deficient boron. That makes this the Lewis acid, right? And then the water here is the Lewis base. And that forms 1 bond. With a negative charge on the boron and a positive formal charge on the oxygen. So that's the 1 new bond that's formed. And so in this, water donates that electron pair to BF3 to form that new bond. Now, Lewis acid-base reactions illustrate a general pattern in organic chemistry. That general pattern is electron-rich species things that have a lot of negative electron density react with electron poor species. And so a Lewis acid is a lot of times called an electrophile. Right? And an electrophile is a way to describe things that are electron deficient or electron poor. Okay. Then we have a nucleophile, and that is what we would call the Lewis base. And this describes things that are electron rich. Right? So in the previous example, BF3 was the electrophile and water was the nucleophile. Okay? And nucleophiles and electrophiles react with each other, just like the opposite charges on a magnet. Okay? So these react with each other. So, when we look at this, I want us to look at a few other just quick example reactions. So, for example, we are going to have a carbocation there. So that's a carbon with a positive charge, and it's going to react with bromine with a negative charge here. And what we find is bromine here is going to act as our Lewis base, but because it's got that negative charge on it, that means there's a lot of negative charge density there. And so we can also just more generically describe that as a nucleophile. Right? And then we've got this positive charge, and so that's electron deficient. So that's going to be our Lewis acid, but more generically, we can describe that as the electrophile. And just like with magnets, where positives and negatives like each other and they get attracted to each other, we see that same thing with atoms here. And so a pair of electrons here is going to jump out, and it's going to be attracted to that positively charged carbon. And so to show that electron kind of pathway, we draw an arrow like this. And it says, hey, look, these electrons are going to form a new bond with this carbon atom. When they do that, we have a new bond shown right there. So that's our new bond that's formed. Now, I want to show another example, right, of a where we have HCl and this molecule right here. And so when we look at this, right, we have hydrochloric acid, which is going to be our Lewis acid. And we need to remember that chlorine is very electronegative, and hydrogen, that makes hydrogen electropositive. So there's this partial positive charge on the hydrogen. And then we need to remember that this double bond has lots of electron density. It's a sigma bond, it's a pi bond. And so there's just lots and lots of electron density there. So because there's lots of electron density there, that makes it a Lewis base, right? So that's going to be a nucleophile. This Lewis acid here is an electrophile, right? And so what you find is that the electrons that make up this pi bond are going to come out, and they're going to grab that proton and pull it back, okay? Similar to what we saw in a proton transfer reaction. And then these electrons are going to go, and they're going to live on the chlorine. And so you end up then with a carbocation, and you have a new bond, right, that's formed right here. I'll get my colors right in a second. Then you also have the chlorine here. Now, we are going to talk about the ins and outs of all of this reaction in chapter 10. So if you are asking questions like, ooh, Dr. Pierce, why'd you put the hydrogen here instead of here? That's fine. And the answer really is has symmetry, so it doesn't matter which side it goes on. But we're going to dig more into that in chapter 10. But what I want to focus on here is this part, right? A nucleophile reacts with an electrophile. These arrows are showing electron movement. When you have a double bond, notice your arrow starts here in the middle of the double bond, right? Lots of negative electron density. It's attracted to something that's partially positive. That's where we see that reaction. Your ability to identify these types of patterns is critically important to predicting reactivity. And you're going to see this trend over and over and over again. So I really want you to succeed. So if you have any questions about this, please stop by my office and ask. I am happy to help.